if you still remember, when we talk about transmission line, there's a ratio associated with the voltage and current, and we call V over I equal to the impedance of the circuit. Same thing happened to an electromagnetic wave. There's a certain ratio associated with the electric field and magnetic field. So in this session, I'm going to tell you the ratio and also the directional relationship between E and H and also K. So we had the guessing solution for the electric field in the last session. And then suppose we have the electric field. The question is, can we deduce the magnetic field from the solution of electric field? And the answer is yes, because the electric field and magnetic field are coupled together. So if you know electric field, supposedly you should be able to deduce the magnetic field. So let's use this formula to begin with. And in this formula, you have F as a scalar and G as a vector. And let's try to put the guessing solution of the electric field, E, into this expression and just replace the G with this electric field. And once you do this substitution, you come up with curl of E equal to this expression. And don't forget that this E, this electric field phasor, is expressed like this. So if you spell out this phasor, then you have this expression. And in this calculation, you notice that you have to do this curl operation on this electric field. And this electric field has a complex exponential. And you come up with this simple result, which has an analogy in the scalar calculation. Remember that when you do a derivative of the r to this exponential minus jkr, you drop down this minus jk and then just leave this the exponential minus jkr unchanged. So I want to use this analogy for you to remember these results. And sometimes some student will get confused or get annoyed by this vector calculations. But if you look into this analogy in scalar calculation, perhaps you can remember this. And now, if you put this and this together, you have this calculation already from this expression. But on the right-hand side of this expression, it tells you that the curl of E can be replaced by this. So if you just put this and this together, then you end up having this expression. And this expression tells you that if you know electric field, you can deduce this magnetic field from this expression. And we can further organize this into a more compact form. If you just do some algebra, then you can write down this expression. The magnetic field now is equal to 1 over eta. This is the, just some factor. And then you have a vector cross product, which is the unit vector along k direction cross with the electric field calculated from the Helmholtz equation. And this means that if you know the electric field, if you know the direction of propagation of the wavefront, and then if you know this eta, then you can write down the expression for the magnetic field. And turn out that this eta is equal to 377 multiplied with this mu r over epsilon r square root. And this mu r and epsilon r are relative permeability and relative permittivity of the material. And the unit of this ratio is ohm. It's just like the unit of V divided by I. And so we call this the factor as the intrinsic wave impedance, which gives you the ratio of H to E. And this expression also tells you the directional relationship between H and E and also K. So remember this right-hand rule. When you have a vector cross product, you can first point your four fingers along the first vector along this AN direction, and then rotate your four fingers toward the second vector. And then the direction of your thumb is going to be the direction of your answer. So it tells you that well, this H field is perpendicular to the K vector and also perpendicular to the electric field vector. But at this moment, we don't know yet the directional relationship between AN and also E. And in vacuum, the relative permeability and relative permittivity is equal to 1. So the intrinsic wave impedance is equal to this value, 377 ohm. And we call this the intrinsic wave impedance in vacuum. And in optics, we often deal with non-magnetic materials. So this mu r is equal to 1 for non-magnetic materials. So this eta now is just the 377 ohm divided by square root of epsilon r. And in optics, we often define this square root of epsilon r to be a symbol n, which is the refracting index of the material. And so when you work on optics problems, you'll be seeing this refracting index quite often. And we can also start from the Ampere's law and try to deduce the relationship between H and E. And often that we propagate the wave in source-free region where you don't have charge, you don't have current. So you can just drop out the Ga in this expression and just deal with the relationship between H and E. And so you apply the same formula, the vector identity, to the calculation again, then you can come up with these results. I'm not going to go through this calculation again because the calculation of this is going to be the same as the calculation we just did on the last 2 pages. And this result also tells you that if you know the magnetic field from your solution, you can deduce the electric field as well. And don't forget there's a proportional factor eta here, which is the intrinsic wave impedance. And this expression also tells you the directional relationship between electric field, magnetic field, and also the K vector. For example, if we look into this vector cross product and set the minus n direction along this direction, and then your 4 fingers will just rotate toward the H direction. Then your thumb direction will be the direction of the electric field. And through the definition of the vector cross product, you also learn that this expression tells you the electric field is perpendicular to the K vector and also perpendicular to the H vector. And in Maxwell equations, there's a Gauss law right here. And in the source-free region, you can also drop this law, the charge density, and write into a value equal to 0. And put down the Guessing solution into this expression. You will get this result, K dot E equal to 0. And this also tells you the directional relationship between K and E, because it tells you that if you project K onto E, or if you project E onto K, you get nothing. So this means that the K and E are perpendicular to each other. And in fact, this conclusion has been obtained from this expression. From this expression, you can also tell that the E and K are perpendicular to each other. So let me summarize a little bit that from our calculations, the first result tells you that if you have an electric field, then you can deduce the value of the magnetic field by using this formula. And the proportional factor is eta, which is the intrinsic wave impedance. But the directions, the relationship from this expression tells you that the magnetic field is perpendicular to the electric field and also the k vector. And then we have the second expression from the Ampere's law, and this also tells you that the electric field is perpendicular to H field and also the K field. And don't forget that the relationship has to follow the right-hand rule. And finally, the Gauss law again confirms that the electric field has to be perpendicular to the K vector. So if I write down the three vectors and draw it on the whiteboard, then you come up with this construction. This construction is consistent with the result from these three expressions. So you could check that, well, if you put your four fingers along the k direction and then do a rotation toward the electric field, then your thumb should follow the direction of the H field. Or if you put your four fingers along the electric field direction and then rotate your fingers along the magnetic field direction, then your thumb should be along the AN direction, the K vector direction. So this is the three-dimensional cartoon for a time harmonic field. Suppose that you have electric field oscillating vertically, then you have the magnetic field oscillate horizontally, and the field will propagate along k direction. And those three vectors are perpendicular to each other. So this name associated with this wave, we call this transverse electromagnetic wave, or simply use this abbreviation, TEM wave. And this TEM wave is the simplest plane wave in space. And you should remember the directional relationship among these three vectors. So I just talked about the wave impedance. And the ratio of the electric field to the magnetic field is equal to eta. Eta is the intrinsic wave impedance. In free space, this eta is equal to 377 ohm. And if you know the electric field from your analysis, you should be able to write down the expression for your magnetic field through this expression. Or alternatively, if you know the solution for your magnetic field, then you can also deduce the solution of your electric field through this expression. And the three vectors E, H, K are perpendicular to each other. And we call this wave transverse electromagnetic wave, or TEM wave. Thank you.